Okay, so we can. Okay, can I get your response? Can you see my screen?
Yes, doctor.
Okay, thank you for that. Okay, so last week we have learned until chapter 4 in the topic of frequency shift keying. Okay, so we can restart again for this topic, FSK. This is about digital modulation techniques where we modulate the digital code word with the analog carrier. Okay, so if you see from if I draw the picture here, the modulator, so we have input in the form of digital code word, logic 1, logic 0, logic 1, logic 0, which are the binary. And we want to modulate this digital code word with analog carrier. Okay, so we have an analog carrier like this. So this is, we can say that this is a VCT. Okay, so when we modulate a digital code word with analog carrier, we are going to produce an output, okay, which is in terms of analog, okay, where we call it as VFSK. Okay, so we are going to produce an analog waveform, okay, in the shape an analog waveform is electromagnetic wave, okay, which carries digital information. So normally when we produce analog waveform, normally we are going to transmit through the wireless medium, okay, through the air or the vacuum. Okay, so if you see from here, the concept of modulation, when we modulate carrier with input, that means the characteristic of the carrier will change according to the input variation. Okay, so that means for this case, the carrier signal, the analog carrier signal, will change its characteristics based on the changes of the input. So if you see, the input can only have two states, either logic 1 or logic 0. That means the analog carrier will have two possibilities of changes. Okay, so in this case, you're going to see later that um, for FSK, the frequency of the carrier change according to the input signal variation. So that is for the FSK. And previously we have learned about ASK, amplitude shift keying. So previously we learned ASK, the amplitude of the carrier change according to the variation of the digital code word input. Okay, so for this case, you're going to see later that the changes of the digital code word logic 1 and logic 0 will change the frequency characteristic of the carrier. Okay, and if you see from here, for so we are learning about binary phase shift keying, BFSK. So BFSK is the short form for binary phase shift keying, where the input is either logic 1 or logic 0. So binary means we have one bit input at a time. Okay, one bit input at one time. So that is a binary phase shift keying. So the general equation for FSK is VC cos 2 pi FC plus VMT delta FT. okay, where you're going to see the difference going to be from the input VMT. Okay, so the input VMT can have two possibility, either logic 1 or logic 0. Okay, so if this is a logic 1, that means it's going to produce a positive uh, output. Okay, a positive output. And if the input is logic 0, it's going to produce negative output. Okay, so from these changes, we can put into the general equations, okay, VFSK. If let's say the input is logic 1, for example, for input logic 1, so we're going to assign VMT with positive 1. Okay, so that means VMT is positive 1. So you can cancel out this one actually. So actually it is a FC plus delta F. Okay, and whenever the input is logic 0, okay, we're going to assign VMT with minus 1. Okay, so minus 1 for the VMT, we can put inside the general equations. That means this is minus 1. Okay, so you can cancel out this one VMT. So that means the equation is VC cos 2 pi in bracket FC minus delta F. Okay, and then the bit rate and baud rate of the FSK is equal. So this statement is important. So that means bit rate is equal to baud rate. What's the difference? Bit rate is the speed of transmission. It shows how many bits we can send in 1 second. Whereas for baud rate shows how many symbol we can send in 1 second. So since this is a BFSK, okay, so for BFSK, binary phase shift keying, the bit rate is equal to the baud rate. Okay, so remember, this is only true for BFSK. Okay, for BFSK. So the calculation of the bandwidth for the FSK is equal to 2 times delta F plus B. Okay, so this is a bit rate or the baud rate, okay, for FSK. And for the signal generation in the transmitter, okay, how can we generate the BFSK signal? Okay, so we can have two oscillator with frequency F1 and also oscillator with frequency F2. And we can have two modulator 1 and also modulator number 2. Okay, so the input is logic 1, 0, 1. Okay, so you put inside the first modulator, and this also pass through another inverter, where the inverter will inverse the logic numbers, okay, the logic bit. So that means 101, if you inverse, is going to be 0, 1, 0. Okay, so this will be insert into modulator number 2. Okay, so then this process happens. So we're going to see that the process happen is actually involve about ASK. Okay, where you modulate with analog carrier. Okay, the analog carrier has frequency F1. Okay, in this example, F1 is larger than F2. Okay, in this example. So the output here is changed according to the amplitude in this case. Okay, so you see the symbol of X. That means we're going to do the multiplication process in time domain. Okay, so when you multiply with logic 1 and logic 0, for logic 1, when you multiply the signal, you're going to produce an output like this. Okay, so this output has a frequency of f1. And then when you multiply with logic 0, the output going to be 0 output, 0 volt output. And then you multiply with input logic 1, so you're going to produce an output signal like this. Okay, so this is similar with the ASK, amplitude shift keying. Okay, and this pass through the adder. And what happened in the second modulator is also the same. Okay, so logic 0, if you multiply with the analog carrier, you're going to produce 0 output. And logic 1, you multiply with uh, uh, the carrier, the analog carrier, so you're going to produce an output like this. So why the shape is like this? This is to show that the frequency of the output is less compared to the frequency f1. Okay, so if the ripple is short like this compared to many ripples like this one, so this is to show that this is a low frequency output. And logic 0 with analog carrier, so you're gonna produce 0 output. Okay, so this also pass through the adder. Okay, so what happened in the adder? In the adder, you will add both signal from modulator 1 and modulator 2. Okay, so we have here an output with high frequency from modulator 1, and then we have low frequency output from modulator 2. Okay, from modulator 2, and then we have high frequency output from modulator 1. Okay, so you're gonna see that the output is changes in terms of frequency. So we have high frequency, low frequency, high frequency, and so on. Okay, so similar with the picture below. And we're gonna see this one. We have this is the waveform for the FSK. So the waveform here, if you see, we have input, binary input, logic 1, logic 0, logic 1, logic 0. Okay, and remember, whenever the input is logic 0, the output will produce a low frequency output. If we compare from the previous example, okay, so you see that the input is logic 1 is going to produce high frequency at the output. For input logic 0, you're going to produce low frequency at the output. Input logic 1, you're going to produce high frequency at the output. Okay, so similar with this one. So input logic 0, you're going to produce low frequency output, where we call it as Fs. Okay, so Fs is actually the lower frequency, which is actually Fc minus delta F actually. Okay, the space frequency. And then for the marked frequency, you see that whenever the input is logic 1, so it's going to produce high frequency output. We call it as a marked frequency. So Fm, the marked frequency, the high frequency, is actually the highest frequency of carrier plus delta F. Okay. So, and then the next is logic 0. Then we produce a space frequency, and then marked frequency for logic 1, and so on. Okay. So this is for the FSK. And we have gone through this waveform. So we have input logic 1, input logic 0, 1, 0, 1, 0, 1, 0. So what happened is that we're going to produce a marked frequency, and then space frequency, marked frequency for input logic 1, space frequency for input logic 0, and then Fs. Okay. And the bandwidth of the binary phase shift keying is equal to 2 times n fm, the frequency of the input plus delta f. Okay, so if you see from the example, the input is up to the fifth harmonics. That means the output is 2 times 5 fm if we have a input up to 5 fm, and then plus delta f. Okay, so this is actually 10 fm plus 2 times delta f for the bandwidth. Okay, this is the bandwidth for the binary phase shift keying. So for the example, determine the bandwidth for the FSK modulated signal when oscillator 1 feeds 270 kilohertz and oscillator 2 feeds 100 kilohertz, and the baud rate is 1000 bit per second. Okay, so you see that we have two different frequencies. One is high frequency, another one is a lower frequency. Okay, so I can say that this 270 is actually representing as Mach frequency, and this 100 kilohertz is actually the space frequency. Okay, and the baud rate, okay, the baud rate, as we have learned previously, the baud rate for FSK, BFSK, is equal to the bit rate. Okay, so the bit rate and the baud rate is equal. So therefore, if you see from here, uh, the baud rate, so this is uh, the baud rate. So that means the question asks you to find the bandwidth in terms of hertz. Okay, so the bandwidth for the BFSK is actually 2 times delta F plus B, as we have learned from the previous slide. Okay, so this is actually equal to 2 delta F plus 2 times bit rate, or the baud rate in this case. Okay, so the B here is actually the bit rate. Okay, since the bit rate is equal to the baud rate for BFSK, so we can make it equal to the baud rate. Okay, so in the initial equations, okay, in the original equation, it is actually the bit rate. Okay, so if you see from here, um, delta F is actually FM, the Mach frequency. Uh, so this is 2 2 delta F. 2 delta F is the carrier swing from the highest frequency to the lowest frequency. So that means this is Mach frequency minus space frequency. And then you plus with the 2 times the baud rate. Okay. So if you see from here, FM, the Mach frequency, minus the space frequency, and then plus 2 times the baud rate. Okay, 2 times the bit rate, or in this case it's a baud rate, so equal to 190 kilohertz. Okay, so this is example of the BFSK, binary phase shift keying. Okay, so in this case you're going to see that the delta F, so 2 times delta F is a carrier swing. So this is carrier swing. Okay, so it is equal to Mach frequency minus space frequency. And this is at the receiver. Okay, this is at the receiver side. At the receiver side, how can we detect the FSK signal? Okay, so we have input FSK. So this is at the receiver side. Okay, so the receiver receive FSK input. So we put inside the power splitter. Okay, so the power splitter will split the input according to the uh, mark frequency and also according to the space frequency. Okay, so this signal pass through the multiplier where we're gonna multiply with a carrier, the same carrier from the transmitter. Okay, the same carrier signal from the transmitter, and we're gonna produce two sideband in this case, lower frequency and high frequency, and then pass through the low pass filter. So the low pass filter will select the low frequency. Okay, and then put inside the uh, data output. Okay, so similar with second multiplier. So this is the first multiplier and this is the second multiplier. Okay, so for the second multiplier also similar. When we multiply the input with carrier, so we're going to produce two sideband, double sideband, and then pass through the low pass filter. So the low pass filter will select this one. Okay, and this one will be converted into data. Okay, this one will be converted into data. uh, 1 1 0. Okay, logic 1, logic 0, logic 1, logic 0. So for picture A, this is for coherent. Coherent means that we have carrier signal during the detection process. Okay, and for picture B is a non-coherent. So non-coherent means that we are not using carrier signal, okay, for the demodulation process. So if you see from here, the FSK input put inside the power splitter, so it's gonna split for the space frequency and also for the mark frequency. Okay, and then put inside the bandpass filter to select the desired bandwidth. Okay, and we produce an analog output. Okay, and then put inside the envelope detector. Envelope detector is like a AM detector where it convert the input, the changes of amplitude into output. Okay, the changes of amplitude from the input will produce a DC output. Okay, in this case, and then pass through the comparator, and then we can have the digital data at the output, logic 1, logic 0, logic 1, logic 0. Okay, and the next one is the probability of bit error for coherent FSK. So coherent FSK is similar with coherent ASK. Okay, the equation is the same, where it is equal to 1 over 2 complementary error function in bracket square root of 1 over 2 EB over N0. Okay, so this one you can find from the table, okay, from the complementary error function table. And then for the non-coherent, okay, non-coherent means we are not using carrier signal for the detection at the receiver. Okay, so the probability of bit error. So remember that this probability of bit error is calculated at the receiver side. So it's measure how many bit, the probability of bit error at the receiver side. Okay, so if the receiver is non-coherent, that means we can calculate the probability of bit error equal to 1 over 2 exponent power of minus 1 over 2 EB over N0. Okay, so this is you can directly use your calculator. Okay, so for exponent function, if you see from your calculator, it is actually you can press shift lon. Okay, if you press shift lon, then you can get the e power of something. Okay, you can put inside the value of minus 1 over 2 eb over n0, and you can get the values. Okay, so the next type of modulation is phase shift keying. Okay, phase shift keying, PSK. So PSK is the type of modulation where we change the phase of the carrier according to the binary input. Okay, so in your syllabus, you are learning about binary input. So previously we have seen about ASK, okay, binary ASK. You also have seen about binary FSK. Now we are going to see the binary PSK. Okay, remember for the binary means that we have one bit input at a time. Okay, so in this case we are using a one bit input. Okay, so if you use the concept of 2 power of k or 2 power of n, okay, k is the number of bit. That means you're gonna have 2 power of 1. Okay, why we use 1? Because the input is one bit at a time. So whenever you see the word binary, okay, binary means one bit at a time. So for binary is a one bit, that means we're gonna have two unique symbols. What is a symbol? The symbol can be either logic 0 or logic 1. Okay, only two possibilities of input, either logic 0 or logic 1 at a time. Okay, so that's why we call it as binary. Okay, so when you have learned previously ASK, FSK, and PSK. Okay, so uh, the way we write the symbol is in the form of emery. Okay, so that means m is the number of symbol. Okay, so if the number of symbol is 2 bits, okay, that means it is a for 2 ASK. Okay, sorry, 2 ASK is what we call as a BASK. Okay, binary amplitude shift keying, one bit at a time. Okay, you also have learned about 2 FSK previously, where we call it as BFSK, binary phase shift keying. And now we learn about BPSK, 2 PSK, or known as the BPSK. Okay, so remember, M can grow bigger. Okay, M is the number of unique symbols. Okay, so if you see from here, the input is binary data, either logic 1 or logic 0. Okay, in this case is 1010. Okay, and then this gonna be put inside the level converter. So remember, this process happen at the transmitter side. Okay, so this is at the transmitter side. Okay, so you're gonna put inside the level converter. So level converter will make the output in terms of, if it is a logic 1, so that means the output gonna be positive. If the input is logic 0, it's gonna convert into negative voltage. Okay, and then positive output. So level converter is to convert from unipolar to bipolar. Okay, and then we put inside the balance modulator. So balance modulator is a carrier signal. with a function of sine omega ct. Okay, so this is actually VCT. Okay, so remember that your input is either logic 1 or logic 0. Okay, so there are two possibilities. So for input logic 1, so this gonna be translated into positive input. Okay, the positive input. And for input logic 0, so this is represented with negative value. Okay, so the output here gonna be two possibilities, either positive sine omega ct or negative sine omega ct. Okay, since we have bipolar over here, positive and negative. Okay, so the output of balance modulator, only two possibilities, either sine omega ct or negative sine. So for sine omega ct, you're going to see that the wave looks like this. Okay, for the negative sine is going to be inverse like this. Okay, so this is negative sine and this is positive sine. Okay, so you're going to see later that the waveform that you're going to generate, either sine wave positive or negative sine, positive sine, negative sine, positive sine, negative sine. So you see that the inversion of signal, positive sine to become negative sine, okay, from positive to negative or negative to positive, you're going to see that the changes is about 180-degree phase shift. Okay, the phase of the carrier change for about 180-degree. Okay, and then pass through the band pass filter, and then you can send through the medium. Okay, so remember, the signal that you send through the medium is either positive sine or negative sine wave. Okay, and whenever when it arrives at the receiver side, okay, so you see that the input is BPSK input, either positive or negative sine omega ct. Okay, so that means the input can be positive sine or negative sine wave like this. Okay, and then put inside the band pass filter to select the desired band and remove the unwanted frequencies. Okay, and then you put inside modulator. So this is a coherent detection where we multiply with the carrier again. Okay, so balance modulator, if you remember, it is a symbol like this. Okay, so we have output. So now the input is positive sine. Okay, either positive sine omega ct or negative sine omega ct. So when you multiply sine square, it's actually you're going to produce double sideband, the upper side, lower sideband, and also the upper sideband at the output of balance modulator. Okay, and then you pass through the low pass filter. The low pass filter will select the lower sideband, the low frequency. Okay, and then you put inside the level converter, and you're gonna produce an output in terms of logic 1, logic 0, logic 1, logic 0. Okay, so what happened here, we're gonna see in terms of mathematical equations like this. Okay, so if you see from here, BPSK input at the receiver, okay, if it is a if it is a positive sign, that means it is actually logic 1. Okay, So we actually receive logic 1, okay, at the receiver side. Why logic 1? So we have to refer to the transmitter side, okay. So if you see, logic 1 is represented by positive sign, logic 0 is negative sign. Okay, so if I rewrite again, logic 1 represented by positive sign, omega ct, logic 0 represented by negative sign, omega ct. Okay, so here, if you receive positive sine wave, that means it is actually logic 1. Okay, so uh, so we know that by default, we know that this is actually logic 1. Okay, so the output of the balance modulator, so sine wave input you multiply with from the carrier, from the local oscillator, so you get a sine square. Okay, so what is sine square? Sine square is here. So sine square is actually over here, sine square. Okay, sine square, when you elaborate the equations according to trigonometry identity, you're going to produce lower sideband and the upper sideband. Okay, so if you see from here, uh, we're going to produce sine square. So you're going to produce, if you see from here, it's become 1 over 2, 1 minus cos 2 omega ct. Okay, so you have this lower sideband, and also this is the high frequency output. Okay, so uh, if you see from here, this is the output of the balance modulator. We have two signal. The first one is 1 over 2. This is the first signal, and this is the second signal. This is the high amplitude. Okay, this is the high frequency. Sorry, not high amplitude, high frequency, 2 times omega ct. So this is a high frequency where this is going to be filtered out at the low pass filter. So when you supply to low LPF, when you supply this signal to the low pass filter, okay, it will remove the high frequency input. So therefore you get positive 1 over 2. Okay, so positive 1 over 2 is represented by logic 1. Why? Because this is a positive values. Okay, and let's see what happens if we receive negative sign. Okay, negative sign, if we see from the transmitter, is actually we are sending logic 0. Okay, so what happened when we receive negative sign? The output of balance modulator, so this is the input, you multiply with the local oscillator signal, so it's going to be negative sine square. Negative sine square, according to trigonometry identity, is going to be negative 1 over 2, 1 minus cos 2 omega ct. Okay, so this is a high frequency output. And if you elaborate, so it's going to be negative 1 over 2 plus 1 over 2 cos 2 omega ct. So this you pass through the low pass filter, LPF. Okay, low pass filter will remove the high frequency input, and therefore the output going to be negative 1 over 2. Negative 1 over 2 is actually logic 0. Why logic 0? Because this is a negative value. Okay, so positive value is logic 1, negative value is logic 0. Okay, so the next topic is about the truth table, phasor diagram, and constellation diagram. Okay, so the first one is truth table, table A. So you're going to see that for input logic 0, the output phase is 180 degree. Why 180 degree? And input logic 1 is 0 degree. So if you see from here, why is it like this? So this is based on the sine wave. Okay, for input logic 1, okay, we're gonna have sine wave like this, positive sine. Okay, so the phase here is 0 degree. And when we have input logic 0 as the input, that means the wave that we're going to produce is like this. Okay, so this is actually 180 degree. Okay, 180 degree changes from the input. Okay, because this is inverse. Okay, so when it is an inverse wave, so it is a 180 degree. So initially is 0 degree, starting from 0 degree, and then input logic 1, input logic 0 is going to be shifted 180 degree. Okay, so this is the truth table. From the truth table, we can also plot the phasor diagram. So phasor diagram is also known as the arrow diagram. Okay, so arrow diagram, you see from here, it has four quadrants. Okay, so we have the first quadrant here, the second quadrant, third quadrant, and the fourth quadrant. Okay, so if you see on the right side, it is a sine. So on the right side is sine wave. Sorry, on the right side is a sine omega ct. So if sine omega ct, so it is actually 0 degree on the right side. Okay, if negative sine, it is 180 degree, so it is the left side here. Okay, so positive sine on the right side, negative sine on the left side. Positive sign is logic 1, negative sign is logic 0. So we're going to have two arrow, one pointed on the right, another one pointed to the left. Okay, and if you see the y-axis, the y-axis is for the cosine cos omega ct. Okay, cos omega ct, above and below is minus cos. We're going to see this later about this. So and then for the constellation diagram is the dotted diagram, where we represent each symbol with a dot. Okay, so here we have two possibilities, either logic 1 and logic 0. Okay, so logic 1 is located at 0 degree over here. Okay, so remember that 0 degree, 90 degree, like this, and 180 degree, 290 degree below, right? So according to the quadrant of degrees, so degrees, 0 degrees is on the right, 90 degrees, this is 90 degrees above, and then 180 degrees on the left. Okay, so this is the second symbol. So the dotted here is actually representing symbol. Okay, so here we have symbol. For BPSK, we only have two dots. Okay, either logic 1 at 0 degree or logic 0 at on the left side at 180 degree. Okay, this is for BPSK, because we have M, the number of unique symbol is 2. Okay, if we go for higher value, higher bit value, if the number of K is higher, that means we're going to have the number of symbol would be more than 2. Okay, so in this case, we only use 1 bit. Okay, and we have 2 unique symbol, 2 dots only. So what's the purpose of these dots actually? So when we go for higher modulations technique, okay, you're going to see that there are going to be many symbols. Okay, And you're going to see that in high modulation techniques, there's going to be many symbols. Okay, many symbols. Okay, so the more the symbols, the higher will be the probability of bit error. However, as a trade-off, we're going to have higher speed of transmission. Okay, remember the higher the number of symbol, the faster would be the transmission speed. Okay, and we're going to consume a lot of bandwidth, but the trade-off is that they're going to be higher chances of bit error. Okay, so there's a more explanation on that matter regarding the number of bit, the number of symbols, and also the relation with the probability of bit error. Okay, so the purpose of this, one of the purpose for this constellation diagram is to see how close is the symbol from one symbol to another symbols. Okay, so from there we can uh, estimate or calculate the probability of bit error. Okay, so that topic for details about high modulation techniques are not covered in your syllabus. So your syllabus is the basic concept of the modulations is up to 1 bit only, where you're going to have two unique symbols, either logic 1 or logic 0. Okay, so this is the waveform of BPSK. Okay, so for input logic 1 is going to be positive sign. Okay, positive sign. Positive sign is like this. Okay, and input logic 0, you're going to produce negative sign. Negative sign starts below like this. Okay, and input logic 1, positive sign. Okay, and then negative sign. For input logic 0, positive sign, negative sign. Okay, so you're going to see here that the changes, okay, the changes here at this point. Okay, so instead of the wave pass through like this, it's going down here. Okay, so this the difference, okay, is actually 180 degree. Okay, so this is to show that the shifted in phase is about 180 degree. Okay, similar at this point shifted, shifted, shifted 180 degree. Okay, and then we have gone through this, the waveform picture above. So picture above here is a waveform. So if you see input logic 1 is a sine wave. Okay, and then input logic 0, you see that input logic 0 is going to be inverse sine wave like this. And then input logic 1, positive sign. Okay, and then input logic 0, negative sign. Okay, and so on. And then in terms of minimum bandwidth, you're going to see that the minimum bandwidth is 2 times n times fm. So since the input here in this example is up to 5th harmonics, so therefore you're going to produce 2 times 5 fm. So this is 10 fm. So the issue is why do we need to multiply with 2? Because we have upper sideband and also the lower sideband. So that's why we have to multiply with 2, okay, to consider the upper and the lower. And in terms of probability of bit error for the PSK, okay, probability of bit error for the PSK. So probability of bit error for the PSK is different from ASK and FSK. Okay, it's a bit different. Okay, so PSK is different from ASK and FSK, where you're gonna see that uh, the probability of bit error is equal to 1 over 2 ERFC in bracket square root of EB over N0. So there's no 1 over 2. Okay, if you remember in ASK and FSK, we have 1 over 2 EB over N0. So now there's no 1 over 2, no half. So that means this one only FSK, only PSK is different from ASK and FSK. Okay, so this is for coherent detection. Okay, so remember we measure this based on the receiver performance. Okay, so these are among the receiver performance parameter, the probability of bit error. And for the non-coherent receiver, okay, non-coherent receiver, the probability of bit error at the receiver side is 1 over 2 exponent power of minus EB over N0. So there's also no 1 over 2 parameters in the equation. So this is for PSK. And the next topic is about digital multiplexing. Again, if you remember in chapter 1, I said that in digital communications, multiplexing is much easier compared to the analog. Okay, why? Because the input, we have only two possibilities, either logic 1 or logic 0, only two possibilities. It's different from the analog. Analog has infinite shape, whereas for digital, we have only two states of probability, either logic 1 or logic 0. So all signals, all input signals can be treated equally, okay, because they only have two possibilities, logic 1 or logic 0. So we can combine it together and share the medium to transmit from transmitter to the receiver side. Okay, so we can do the multiplexing easily. So multiplexing, we can multiplex the signal in the transmitter side, okay, and then we send through the medium, and then at the receiver side, we can do the demultiplexing to reduce the output. So that's why we can have many inputs. In digital systems, we can have many inputs and combine it together and send it through the shared medium. So for the multiplexing method, there are a few methods of multiplexing. The first one is frequency division multiplexing. So frequency division multiplexing has been explained in chapter 1 previously. Okay, briefly explained in chapter 1, where we divide the bandwidth. Okay, so we have a big bandwidth. Okay, and we divide the bandwidth in small portions. Okay, we divide the bandwidth in small portions. Each small portions of bandwidth is assigned to different users. Okay, user 1, user 2, user 3, and so on. Okay, so we are dividing the frequency in this case. Each frequency is given to a specific input user. Okay, so if you see from here, for the FDM, okay, so here we have a 1 megabit digital. So we put inside the 16-bit QAM, okay, to produce an output of 200 kilohertz, okay, 200 kilohertz of analog output, and here also 250 kilohertz, 250 kilohertz, 250 kilohertz. Okay, so with this, we have 4 different sets of input frequencies, okay, where we can combine it. Okay, we can combine it together to share a 1 megahertz of bandwidth link. Okay, so the link can cover up to 1 megahertz. So that means we can have up to 4 input. So 250, if you multiply with 4, you're going to get 1 megabit, 1 megahertz. Okay, 1 megahertz of total output. Okay, where we can share the medium. And another one is what we call as a wavelength division multiplexing. So wavelength, if you remember, wavelength is lambda. Lambda is equal to C over F. Okay. So WDM is similar with the FDM, where we divide the input signal according to the lambda. Okay. So WDM is normally used in the fiber optics transmission. Okay, so where we divide the input according to its wavelength. Okay, so wavelength number 1, wavelength number 2, and number 3, and so on. Okay, so if you see from here, we divide the input into uh, different wavelength. Wavelength 1, lambda 1, lambda 2, and lambda 3. And we multiplex together so that the signal can be lambda 1 plus lambda 2, lambda 3. So we can share the medium for all the 3 different signals. And then at the receiver side, so this is transmitter, this is receiver. At the receiver side, we can demultiplex the signal into 3 different output, lambda 1, lambda 2, and lambda 3. Okay, so this is WDM, where we divide the signal according to the wavelength. And then TDM. Okay, so this is TDM, time division multiplex. In this case, we divide the input according to the time slot. Okay, so each input will occupy a portion of the time in the link. Okay, so if you see from here, we have 4 different inputs. This one from computer, for example. So we have COM1, COM2, COM3, COM4. So each of these will transmit signal at a different time slot. For example, if you see from here, the input number 4, input number 3, input number 2, input number 1. So this is a time slot. Okay. So we have different time slot can be occupied by the different input data. Okay. And then at the receiver side, we can do the demultiplexing and produce the original separation of output. Another one is code division multiplexing. So if you see from this one, code division multiplexing is normally used for in the 3rd generation of cellular communications. Okay, the 3G communication system previously it used a CDMA, and then when we move to the 4G, we have a wideband CDMA, and then 5G is going to use also code and space time divisions. So that one is a high level of modulation techniques. So CDM is a high level modulation techniques where we assign each of the input user with a unique code. Okay, we assign each of the input user with a unique code. Okay, so they can share a same frequency, but they have a different code. Okay, so now we are playing with frequency and code. One frequency can have different codes. Okay, so within one frequency, it can be shared with a few number of users. Okay, so they are not overlapping because they have a orthogonal code or pseudo-random code. Okay, so they are not overlapping each other. because they have a different codes, even though it is a same frequency. So CDMA is not covered in details in your syllabus. Actually, the topic is it's a big topic actually in the communication system about CDM, where we learn how can we assign a specific code for each of the user, and also how can we give the frequency numbers. Okay, so in this case, if you see, I can say that we can have three axes. So this is frequency, time, and the other one is code. Okay, so we can have three axes of this one. And actually we have another one is space. The fourth axis is space. Space, in Malay we call it as ruang. So different space we're going to assign with different codes and so on. So that one is a high level modulation techniques. So why do we have many types of modulation techniques like this? So in modern communication systems, we try to support many number of users. Okay, remember that the number of users is keep on increasing. Okay, whereas the bandwidth is very small. Okay, in order to share the small bandwidth with many users, we need to use high level modulation techniques, okay, to support all the users. Okay, so if you see that even in UTHM, we have thousands of users. So we need to accommodate these thousands of users within a limited bandwidth. So in order to do that, we need to have a high level modulation techniques so that we can cover all the users, and the users can have a good quality of signal transmission and reception. Okay, so in that case, that's why the modulation techniques keep on improving so that we can support many users and have high speed of transmission with low probability of error. Okay, that's among the objective. Okay, so limited bandwidth, large number of user, and the user wants to have a high speed transmission and reception with a good quality. Good quality means low error. So that means the modulation techniques is very important so that we can optimize the bandwidth, okay, with a lot of user, high speed transmission, and low bit error. So if we mention about the bit error rate, BER, so this is defined as the number of incorrect received bit divided with the total number of transmitted bit. Okay, so you can say that, for example, within 1 million of total transmitted bit, there's a 1 bit error, for example. Okay, so 1 bit error, for example, 1 bit incorrect divide with total number of transmitted bit, 1 megabit, for example. Okay, so this is 1 times 10 power of minus 6. Okay, so this is the example of bit error. So the number of incorrect bit divide with the number of transmitted bit. Okay, so bit error rate, the lower the bit error rate would be better. Okay, the lower the bit error rate would be better. So ideally, we don't want any bit error, ideally. However, in the real world, there's always a bit error. So the receiver has the capability to detect the error and make the corrections. Okay, so that one is through the coding techniques. Through the coding techniques, the receiver is able to detect which bit is in error and then make the corrections. Okay, so this process happens very fast, okay, at the receiver side. So the receiver has the capability to detect and make the corrections. How to do that is through the coding techniques. So that coding techniques is what we call as a channel coding techniques, which is not covered in your syllabus. Okay, it is covered in different subject. Okay, so in the digital communication system, we are using channel coding in order to be in order to able to detect the bit error and make the corrections. Okay, so that's one of the beauty of the digital communication systems. Okay, where we can have a very good quality of transmission and reception of signal. Okay, compared to the analog. So this is the last slide for chapter 4. Okay, and we can move to chapter 5. Okay, so I will start chapter 5. Before that, can I get your response? Are you still there? Can you see my screen?
Yes, Doctor.
Okay, thank you for the response. Sometimes it feel weird because it's as if I'm talking to the screen. So I don't know what are you doing? Are you listening? Are you seeing the slide or not? So you have to give a response from time to time so that we can have a good discussion about this. So the next topic is the last topic. Okay, this is the last chapter: transmission line, antenna, and wave propagation. So you see that there are three big topics here: the transmission line, the antenna, and the wave propagation. So if I draw my favorite picture again, the transmitter, okay, and here we have the channel, and then we have the receiver side, okay. So this one, so now what we're gonna learn here is that the transmission line is this one, the transmission line, the wire, okay. This is the transmission line from transmitter to the antenna and antenna to the receiver. So this is also a transmission line. Transmission line can also direct connection from transmitter to the receiver. Okay, so that one is transmission line, wired transmission line. Transmission line can also be the wireless medium also. Okay, the wireless medium, also the transmission line. Okay, remember the word transmission line can be wired transmission or the wireless transmission medium. So these reflect the medium. And then the antenna is this one. We have the transmitter antenna and we have the receiver antenna. Okay. And then the wave propagation. Wave propagation is we're going to learn about the characteristic of the wave that travels from transmitter to the receiver side. Okay. So the wave, we're going to learn about the characteristic of the wave that travels from transmitter to the receiver. So you see that in chapter 5, we are not learning anymore about the process that happens inside the transmitter or the processes that happens at the receiver side. We are looking at the out at the we are looking outside of the transmitter and receiver systems. Okay, in chapter 5. So this chapter 5 divided into three main topics. Transmission line, you're going to learn about types of transmission line electrical characteristic, matched and unmatched transmission line. Antenna, we have antenna characteristic, basic wired antenna, types of antenna. And the last one is the wave propagations, electric wave, attenuation absorption, optical properties of the radio wave, and free space loss and link analysis. Okay, so If you see from here, actually, this chapter 5, can be divided into three different subjects in BEJ program. Okay, so transmission line, we have E EMC. So we have a EMC subject, electromagnetic compatibility subject. Antenna, we have antenna subject. Okay, antenna subject. Wave propagation, we have wireless and mobile communication subject. Okay, so chapter 3 is a summary of three different subjects. For BEJ students, especially for the communication students, they're gonna learn about these three subjects, three different subjects. Okay. So this is again my favorite picture. Okay, the transmitter and the receiver. Okay, so here this is very important. So you have to know about this picture. Okay, so if you look from the transmitter side, okay, the transmitter side produce power. Okay, the output power from the transmitter is what we call as PT, power from the transmitter. Signal is passed through the transmission line to the antenna. Within the transmission line, there's going to be losses. Okay, losses in this transmission line, in the transmitter transmission line, is what we call as LT. So LT is normally the losses in terms of decibel per unit length. Okay, normally the losses is represented in terms of dB per unit length. Okay, then this is passed through the antenna. So the input power to the antenna is what we call as P input. Okay, P input to the antenna. And in the antenna, okay, most of the power will be used for to radiate the signal into the wireless medium. So the power that we use to radiate the signal is what we call as P radiation. Okay, some of the input power is dissipated as a heat. Okay, some of it will be losses due to the heat. And uh, this transmitter antenna has a gain GT. Okay, so the signal is transmitted through the medium. Okay, and you're gonna see later that the wave that we transmit is in the form of spherical wave. Okay, towards the receiver. So the EIRP is actually the power multiplied with the gain. Okay, power multiplied with the gain. And then at the receiver side, we're going to have power density. Okay, power density shows how strong is the signal in this receiver area. Okay, so we're going to see the strength of the signal, the strength of the signal at the receiver side is what we call as power density, power per unit area. So this is actually power divided with the area, luas kawasan, okay, area of a space. So the area you're going to see later is depending on the distance from transmitter to the receiver. Okay, then the antenna at the receiver side has a gain of GR, and the output power from the antenna is what we call as P out. So this signal is passed through the transmission line, and this transmission line has a losses, and these losses is represented as LR. So losses here normally in terms of decibel per unit length. Okay, for example, decibel per meter. Okay, so depending on the length of the transmission line. And finally, the power received by the receiver is what we call as PR, received power. Okay, so we go through the first one at the transmission line. Again, the transmission line here can remember the transmission line means the medium of transmission. Medium can be categorized into two categories, unguided and guided transmission. Guided medium is referring to the wired transmission. Okay, so the word guided means that the signal is guided from one point to another point. So that means it is through the wired transmission. So wire can be copper wire, optical fiber, cable, and other types of cables that we can use, okay, for the transmission. Unguided transmission is the wireless. The word unguided means the signal is not guided from one point to another point, so we call it as unguided. Unguided simply as wireless transmission. So wireless medium is, for example, the air or the free space or the vacuum. Okay. So for the guided transmission line, the wired transmission line, we can categorize into three categories: balanced transmission line, unbalanced transmission line, and also the balloon transmission line. So balloon means that balanced to unbalanced. So if you have uh, balanced transmission line and also unbalanced transmission line, you want to connect both of it, you need to use the balloon. Okay, so balloon is like a connector to connect the balance to the unbalanced transmission line. So balanced transmission line is a two-wire transmission line. Okay, one conductor carries the signal while the other conductor carries the return path. So this is the balanced transmission line like this. Okay, it has a two-conductor transmission line. What is the example? So this is the example of a balanced transmission line. For example, here is unshielded twisted pair and shielded twisted pair. Okay, so you see that we have two conductor, okay, in the balanced transmission line. So this is the unshielded twisted pair. So the twist pattern result in a reduction in electromagnetic interference, EMI, and radio frequency interference. Twisting the cables also reduce the crosstalk between the pair of cables. Okay, so that's why we twist the cables in order to reduce the EMI and RFI. Okay, so there's a purpose why we always twist the cable. Dia bukan suka-suka untuk twist. So there's a purpose for twisting the cables. Okay, and this is a shielded twisted pair where we have the sheath at the outer space, outer layer. The outer layer is have a shielding. This is what we call as shielded twisted pair. Okay, so sheath, we have another shield. So this is in order to reduce the interference from another cables. Unbalanced transmission line is the wireless. Sorry, unbalanced transmission line is a single conductor cable. Okay, it's a single conductor cable, unbalanced transmission line. So here you're going to see that we have only single conductor in the cable. Okay, single conductor. Single conductor, if you see from this, this is an example of coaxial cable. So coaxial cable has a single conductor. Okay. And then we have coaxial concentric transmission line. So this is an example of the wire. And then a balloon. Balloon is the balanced to unbalanced transmission line. So this is like a connector to connect both types of balanced and unbalanced transmission line. So if you see from here, this is the example of balloon. Transformer balloon. If you see from here, we have unbalanced input, okay, from the coaxial cable. We want to connect with the balance output, okay. So that's why we have a transformer balloon over here to connect the unbalanced to the balanced transmission line. And then here we have the bazooka balloon, okay. So bazooka balloon here, if you see, we have over here is a unbalanced transmission line over here, and we want to connect with the balanced transmission line over here, okay. So that's why we are using the balloon, okay. This is the balloon to connect the unbalanced to the balanced transmission line. So among the commercial uh, commercial product for this balloon is like this one. For example, passive video balloon BNC connector for CCTV camera coaxial cable adapter. Okay, so this is among the balloon. And another one is balloon for antenna system. So you see that we have one input, uh, another one is a one input and also connected to two output like this. So if you see from here, this is similar with the balloon BNC. So we have two, this one is for the balanced output, and here is a unbalanced. Okay, similar with this one. So this one is one for the unbalanced, another one is for the balance. Okay, so that's why from one conductor we want to connect to the two different conductors, so we need to have the balloon. So the characteristic of the transmission line, the characteristic of the medium, okay. So we can see the characteristic impedance, the velocity factor, and also the standing wave ratio, SWR, okay. So transmission line can be described in terms of lump elements, in terms of resistance R, in terms of inductive L per unit length, and conductance and capacitance. Okay, that means a wire, this wire or cable can be represented in terms of R, L, G, and C parameter. Okay, so when we do the circuit, okay, we can represent the transmission line in terms of R, L, G, and C parameter. Okay, C parameter. So this looks like this. Okay, so this is what we call as a transmission line equivalent circuit. Okay, where it has the R, L, G, and C parameters. This is the lump elements. Okay, so transmission for a long transmission line, it is consists of R, L, G, and C parameters, which is arranged repeatedly. Okay, so we have one section, another section of R, L, G, and C parameters. Okay, so for your information, this is for the two-wire parallel transmission line equivalent circuit. Okay, so this picture has been asked a few times in the previous semester final exam. Okay, we have asked this question where we ask the students to sketch the transmission line equivalent circuit. Okay, so it must consist of R, L, G, and C, and it is a repeated section like this. So this has been asked a few times. I can say also many times in the previous semester's final exam. Okay. Uh, we can go to the this one, table 1.2. Okay. So we're gonna see about R, L, G, and C. Okay. So this one we can skip this one. This one is okay. It's actually okay. Characteristic impedance. So this one you can omit this one for a while and move to the next topic is the characteristic impedance. So characteristic impedance is defined as the impedance seen looking into infinitely long transmission line. So this is referring to the picture on the left. Okay. So picture on the left, you're gonna see that for a long transmission line, so the characteristic impedance Z0 is impedance in looking into the infinitely long transmission line. So that means the characteristic impedance is the same for any points in the transmission line. Okay, characteristic impedance is a constant impedance for that specific transmission line. Okay, or if we have a finite length of transmission line, okay, the characteristic impedance is the impedance seen looking into a finite length of transmission line that is terminated in a purely resistive load with resistance equal to the characteristic of the transmission line. Okay, so that means it is terminated in a purely resistive transmission line where the resistive is equal to the characteristic impedance. So characteristic impedance is a single unit parameter Z0 where uh, it is the same for any points in the transmission line. Okay, regardless from any point of the transmission line. So the characteristic impedance is the same. So this is a constant parameter Z0, which is for that specific transmission line. Okay. So characteristic impedance uh, can be calculated using a few sets of equations. Okay. So in short, we can say that I can say that the transmission line, sorry, the characteristic impedance is the impedance of the transmission line. Okay, the impedance of the transmission line. Simple as that. Okay, so it is can be calculated using a few sets of equations that we're going to see later about this. Okay, so this also has been asked previously in the previous semester's final exam about the definition of characteristic impedance. Okay, so if you uh, I can say that simply the characteristic impedance is the impedance of this transmission line. Simple as that. Okay. So for a maximum power transfer from the source to the load, no reflected power, the transmission line must be terminated in purely resistive load equal to the characteristic impedance. Okay, so in order to make sure that for maximum power transfer from source to the destination, we must make sure that the load impedance equal to the transmission line impedance or the characteristic impedance. Okay, so if you see a single section of transmission line which consists of R, L, J, and C parameters, where at the end we have a uh, load impedance equal to the characteristic impedance. So in order to make sure maximum power transfer from source to the load, okay, we must make sure that the load impedance equal to the characteristic impedance. Okay, otherwise, if it is not equal, okay, if it is not equal, then this is a they're gonna be a losses. Losses here means they're gonna be a reflected wave from the load to the source. Okay, there's gonna be reflection from load to the source. This is what we consider as the losses. Okay. So how can we uh, so about these issues about the uh, load impedance equal to the characteristic impedance. So this is what we call as the match transmission line. Match transmission line. Match transmission line means that the characteristic impedance is equal to the load impedance, where we're going to have a maximum power transfer from the source to the load and no reflection. If it is an unmatched transmission line where the load impedance is not equal to characteristic impedance, so this is unmatched. Unmatched transmission line. Unmatched transmission line, there's going to be a reflected wave from load to the source, where this is considered as losses. Okay. So how can we calculate the characteristic impedance? So characteristic impedance, the general equation is Z0 equal to square root of R plus J omega L multiply 1 over G plus J omega C. Or we can rewrite it again as R plus J omega L divide with G plus J omega C. So this is the general equations uh, for the characteristic impedance. So these general equations we can simplify for two scenarios. Okay, the first scenario is for a low frequency transmission. Okay, for low frequency transmission, the resistance will dominate. Okay, the resistance will dominate. Then we can simplify the equation to become Z0 equal to R over G. And for the high frequency transmission, the inductance and capacitance will dominate. That means the characteristic impedance is equal to square root of L over C. So how big and how small, how low? So normally this is roughly around below below 30 megahertz is considered as low frequency, and above 30 megahertz is considered as high frequency. Okay, so normally most of the time we use the high frequency transmission. Okay, that means the characteristic impedance is equal to square root of L over C. Okay, so this is a common equation that we use to measure the characteristic impedance. Okay, so characteristic impedance can also, so let me make it as this is the first one, the first equations, the second equations, okay? And I can say that this is also the third equation of characteristic impedance. It can also be calculated as the source voltage divided with the transmission line current, okay? So V over I, okay? So you're going to get the characteristic impedance, okay? And if you see from here, the characteristic impedance uh, can also be calculated based on the uh, transmission line parameters, okay, transmission line dimension, okay. So previously we are calculating the characteristic impedance based on the R, L, G, and C parameter, based on the resistive, the inductance, the capacitance parameter. However, the characteristic impedance can also be calculated based on the dimension properties of the transmission line. For example, for a two-wire parallel transmission line, we can measure the characteristic impedance to become 276 log D over R, where D is the distance between the centers of two conductors and R is the radius of the conductor. What is this actually? So this is referring to picture A, okay, where the distance from two different conductors. So this is a two-wire parallel transmission line. So the distance between two conductors is D, and the radius, okay, the radius of each conductor with the what we call with the radius and also the dielectric is what we call as a R. So D and R is in terms of meter. Okay. So this is D in terms of meter, R also in terms of meter. So you get this value in terms of ohm. Remember the characteristic impedance, the unit is in terms of ohm. And then for a coaxial cable, it has a different equation where this is the characteristic impedance is equal to 138 divided with square root of epsilon r log d over d. D is the diameter of the insulating material in meter. Small d here is the diameter of the inner conductor, and epsilon r is the dielectric constant of the insulating material. So it depends on the types of the material for the epsilon r. So if you see the picture is picture B over here, where the conductor is over here. This is the conductor, and over here is the dielectric materials. Okay, the dielectric materials. So the diameter from end to end is capital D over here, and the small d is the diameter for the conductor only. Okay, so the diameter of the cable is capital D. The diameter of the conductor is small d parameters. So you can put inside the values, so we can get 138 over epsilon r log d over d. Okay. So if we want to see the, and again, you don't need to memorize this equation. Okay, this equation should not be memorized. It will be given in the final exam. Okay, so different kind of wire will have a different equations. Okay, we'll have a different equation for the characteristic impedance based on its dimension and also the dielectric materials. Okay, so I can say that this is equation number 4. This is equation number 4 for the uh, characteristic impedance, which is based on the dimension and also the type of materials. Okay. So for the example, determine the characteristic impedance for a dielectric two-wire parallel transmission line, where you are given D over R parameter ratio is 12.22. Okay. So according to the equations, that means you are using this one, D over R, the first one here. So 276 log D over R. Okay, so 276 log, this is D over R, 12.22. So you get 300 ohms. Okay, and then what? Then determine the characteristic impedance for RG59A coaxial cable with the following specifications. The diameter of the conductor is 0.025 inches, and the diameter of the whole cable is 0.15 inches. Epsilon r, so you can correct this one. This is actually epsilon subscript of r, so it is equal to 2.233. So in the, if you see, this is using the inches, inches. So this is I can say that this example comes from the American textbook, where they use the inches, feet, and so on. So in for us, we are using the standard unit, where it is in terms of meter. Okay, so if you want to use in terms of inches, that means you have to make sure all the length is in terms of inches. So that's why the ratio, okay, the ratio here is D over D, okay, inches over inches, so you can cancel out the units, so no problem. So that's why 138 over epsilon r square root of 2.23 multiply with log d over d, so you get 71.9 ohms. Another example, example 3. So example 2 is straightforward, no problem. Example 3, determine the characteristic impedance for RG59A coaxial cable with the following specifications. L equal to 0.118 microhenry per feet. And another one is capacitance 21 picofarad per feet. Okay, so you are given only L and C parameter. There's no other information given. Okay, so in this case, what you can do is Z0, the characteristic impedance, is equal to square root of L over C. Okay, so this is from the previous. If I go back, this is from equation number 2. Okay, L over C. So I go back to the slide. So square root of L over C, L is a 0.118 microhenry per feet, divide with 21 picofarad per feet. Okay, so if you want to use feet, that means both L and C must be per feet. If you want to use per meter, that means both of it should be in meter. Okay, normally in the question in the final exam, we will give the parameter in terms of standard unit, which is in terms of meter. Okay, so that's why here, if you see, the calculation will produce 75 ohm. Okay, so this is for example 3. Okay, so I think we can take a break for a while. Um we can take a break until 1 p.m. Is it okay? Can I get your response? Are you still there?
Boleh Doktor.
Okay, so we will continue again at 1 p.m. Okay.
Okay.
Okay, so it's already 1 p.m. We will continue again. Can I get your response? Are you still there?
Yes,
Yes,
doctor.
Yes, doctor.
So, we continue with the next topic is another parameter in the transmission line is what we call as the propagation constant. So propagation constant, gamma parameter, is a measure of the change undergone by the amplitude of the wave as it propagates in a given direction. And the equation is gamma equal to square root of r plus j omega L multiplied with g plus j omega c. And it can be written also as gamma equal to alpha plus j beta, where alpha is the attenuation constant, a function of distance, which determines how the voltage or current decrease distance along the transmission line. And the unit for alpha parameter is Nepers per unit length. Another parameter is the beta. Beta is the phase shift constant, a function of time, a distance, and determine the phase angle of the voltage or current variation with distance. And this beta parameter, the unit is in terms of radians per unit length. Okay. So the parameter of beta we can calculate as 2 pi over lambda. Remember, lambda is equal to C over F. And this is the first equations. The second equations, we can also calculate lambda equal to omega times square root of LC, where the omega is actually 2 pi F parameter. Okay. Um, so after propagation constant, we can see another parameter in the transmission line, which is the wave propagation. So there is a parameter what we call as a velocity factor. Velocity factor is known as a velocity constant. Define the ratio of actual velocity of the propagation in the medium known as Vp. So Vp here is the actual velocity of the wave that travel through the transmission line. And we can divide the actual speed or actual velocity with the speed of light. So that means Vf is equal to Vp. Vp is in terms of meter per second. It is a velocity, the speed, divide with the speed of light, also in terms of meter per second. Okay, so Vf uh, is the maximum value of Vf is equal to 1. Okay, if the speed of the wave is equal to the speed of light, that means velocity factor equal to 1. So I can say that this is the first equation of velocity factor, which is based on the ratio of actual velocity, actual speed of wave in the medium, divide with the speed of light. We can also measure the velocity factor based on the dielectric medium, okay, dielectric materials, epsilon r, where velocity factor is equal to 1 over square root of epsilon r. So this is a ratio of parameter from 0.1, from 0 until 1. Okay, epsilon Vf is a ratio, so it is actually from 0.001 until 1 values. So the value maximum is the maximum value of Vf is less than 1, equal or less than 1. So epsilon r is a dielectric constant. or the relative permittivity of a material. And the common range of the electric constant is between 1/2 until 2.8, giving the velocity factor between 0.6 to 0.9. Okay. And then the phase velocity or the actual velocity. So previously we have seen that Vp from this equation, Vp is equal to C multiplied with the velocity factor. Okay, so this is considered as the first equation. We can also calculate the phase velocity or the actual velocity of the wave by using the L and C parameter. Okay, so it is equal to 1 over square root of L over L times C, 1 over square root of L C. So this is the unit is in terms of meter per second. Okay. So if you see the relationship between velocity factor and the dielectric constant. Okay. So VF, we know that VF is equal to VP over speed of light. Okay. So that means uh, so the higher the value of velocity factor, uh, the higher the value of velocity factor means that the higher of uh, phase velocity. So if you see from here, the VF is from vacuum until glass materials, and you're gonna see that the value of VF is reducing. Okay, when we use a different kind of materials. So you can see that in vacuum, okay, in vacuum, the the speed of the wave is equal to the speed of light. Okay, when Vp equal to the speed of light, that means Vf is equal to 1. So the wave travels in a very fast speed in the vacuum. However, in air medium, you're going to see that the phase velocity, the actual velocity of the wave is slightly less than the speed of light. So that's why you get the value 0.099997. Okay. And when we use different kind of materials, Teflon, uh, polyethylene, and until glass, okay, you're going to see that, for example, in glass, the speed of the wave that travel in the glass medium is slower, much slower than the speed of light. Okay, so therefore the velocity factor is 0.3651. And if you see from the relative dielectric constant parameter, epsilon r parameter, so uh, for vacuum, the relative dielectric constant parameter is equal to 1. So the higher the value of dielectric constant, you're going to see that the phase velocity becomes smaller. Okay, so the higher the higher the wait, the higher the value of epsilon r, the lower would be the speed of the wave. Okay, so the speed of the wave becomes smaller. That's why the velocity factor becomes smaller. Okay, so in glass, the medium is more dielectric, okay, compared to the other types of medium. So when the dielectric material is higher, that means the speed of the wave that travels through the medium will become slower compared to the speed of light. Okay, so ideally, if you see from here, if you want to have a very fast transmission, that means you have to use vacuum of the air. Okay, so vacuum and the air is one of the good wireless medium for transmission. Okay, so let's do another example. Okay, let's do another example. An RG59A coaxial cable operates at a frequency of 900 megahertz and has the following specification: L equal to 0.118 microhenry. So this is actually microhenry per feet, and the capacitance is 210 picofarad per feet. Okay, so the first parameter, the first question asks you to find the phase constant beta. Okay, what is the phase constant? So beta parameter is actually from the gamma parameter. So the alpha parameter is the attenuation constant, while beta is the phase shift constant. Okay, so the question asks you to find the beta parameter. So since you are given L and C parameter, that means we can use the second equation of beta, omega times square root of LC. Okay, so if we go back to the slide, so that means beta, the phase constant is omega times square root of LC. Okay, so this is 2 pi f, 2 pi, 2 pi f. Okay, so in this case, please correct the question. Okay, so this is supposed to be 300. Okay, 300 megahertz. So 300 megahertz. Okay, so that this is similar with the question, 300 megahertz. So it's not 900. So please correct the question. So this is supposed to be 300 megahertz. Okay, so 300 megahertz times 2 pi times square root of LC. Okay, since we use same per feet, so you're gonna get 9.38 radian per unit length. In this example, the unit length is feet. So that's why you're gonna get in terms of feet. Okay, I'm not sure the answer is correct or not. You can try 2 pi. So first trying to find this 0.118 micro multiplied to 10 pico, and then square root answer multiplied with 300 mega multiplied with 2 pi. So 9.3832 radian per unit length. So remember, the unit length here is feet. If the unit length is in terms of meter, so you can use a meter. Okay. The velocity in the line. So velocity in the line means the speed of the wave in the transmission line. So the velocity of the wave in the transmission line is equal to. So if you see from here, there are a few equations for the phase velocity. So if we go back to the previous slide, okay, if I go back to the previous slide, so you see that the phase velocity can be calculated using C times VF, or you can calculate based on LC parameter, 1 over square root of LC parameter. Okay, 1 over square root of LC. So since we are given LC parameter, so you can use it. Okay, so 1 over square root of L times C, 1 over square root of 0.118 micro times 210 pico. So this is per feet. Okay, so that means the output that you will get is actually 2 times 10 power of 8 feet per second. Okay, so don't worry. If this come out in the exam, normally we will give you in terms of meter per second. Okay, since this is from the American textbook, so they are using feet. So that's why we are using feet per second. Okay, since the original here is feet per second, sorry, per feet, the length is feet. That means we're gonna use the length also feet. Okay. And the third question asks you to calculate the dielectric constant of a coaxial cable. The electric constant is the epsilon R parameter. Okay, so epsilon R parameter, how to calculate the epsilon R parameter? In this example, so if you see from the previous slide, if I go back, epsilon R can be calculated based on VF parameter. Okay, epsilon R can be calculated based on the VF parameter. So if you go back here, this slide, so first we have to find the VF parameter, this one. So VF is velocity, phase velocity, the actual velocity divided with the speed of light. So this is 2 times 10 power of 8 that we already obtained from the previous. In this example, they are assuming that the speed of light is equal to 3 times 10 power of 8 feet per second. Okay, in this example. So normally in the final exam, we will give in terms of meter. So that means 3 times 10 power of 8 meter per second. But in this example, they assume that the speed of light is 3 times 10 power of 8 feet per second. Okay, so when you divide the phase velocity divide with the speed of light, so you get 0.6666. Okay, so that means this is for VF. So in order to find epsilon R, so we know that the equation related to VF and epsilon R, so VF is equal to 1 over square root of epsilon R. So in this case, you see that epsilon R is equal to 1 over square root of 1 over VF. So this is square root of 1 over 0.666. So you get 1.23. Okay. So the epsilon R here is calculated based on the velocity factor. So we find the velocity factor and then we can put inside the equation. So we get the answer 1.23. Okay. So after this example, we're going to see about the standing wave. Okay. Standing wave. So the word standing wave means that the wave looks like as if it stands on a flat surface. Okay, when we stop the time, when we stop the time at a certain time, we stop the at a specific time. When we stop the time, we can see that the wave looks like as if it stands on a flat surface. So that's why the word standing. Okay, so when Z0, the characteristic impedance equal to load impedance, all incident power is absorbed by the load. Okay, so we have incident power. Incident power is from power that transfer from source to the load. This is what we call as incident wave. Okay, which is already defined here. The incident wave is the wave that travels from source to the load. And reflected wave is a wave that travel from load towards the source. Okay, so when characteristic impedance is equal to the load impedance, that means all of the incident wave power will be absorbed by the load and there's no reflection. This is what we call as match transmission line. Okay, so that means there's no reflected wave during the match transmission line. However, when load impedance not equal to the characteristic impedance, there's going to be reflected wave. That means not all of the incident wave will be absorbed by the load. However, this some of the wave will be reflected back to the source. Okay, so only during the unmatched transmission line there's going to be a reflected wave. Okay, so this reflected wave is considered as the losses actually. Okay, because ideally we want all the incident wave to be absorbed by the load. But since it is an unmatched transmission line, so there's going to be reflection, which is considered as the losses. Okay. So if we see from here, the graph A here is what we call as the incident wave, the wave that travels from source to the load. And since the load impedance not equal to the characteristic impedance, what happened is that we're going to have a reflected wave. Picture B. Picture B is the reflected wave. So this is incident. I can say that this is incident. And picture B is the reflected wave. Okay. So based on incident and reflected wave, the combination of incident wave and reflected wave, we produce standing wave, picture C. So picture C, okay, picture C is actually picture A plus B. Okay, when picture A plus picture B, okay, so the wave in picture A plus the wave in picture B. That means incident wave plus reflected wave will produce the standing wave in picture C. So picture C is actually the combination. Okay, the standing wave here, okay, the standing wave is actually a combination of incident and reflected wave. Okay, so you see that the wave is actually we stop it in time. At specific time, we freeze the wave at specific time. We're gonna see that the wave looks as if it stands on a flat surface. Okay, seolah-olah dia berdiri pada satah yang rata. Okay, so this is only, we can see this only if we stop the time. Okay, if we freeze the wave on, at a specific time, we're going to see this phenomena. Okay, so for standing wave, there's a parameter what we call as minima. Minima is this one. So minima here is not zero actually. So minima here is the minimum value, okay, which is known as knots, the name as knots, okay, the minimum. And each minima is separated by lambda over 2 distance, okay, from one knot to another knot is separated by lambda over 2 meter. Okay, lambda over 2 meter. And another parameter is what we call as maxima. The maxima is this one. Okay, I can say that this is the maxima from a maximum point. Okay, the maxima or the anti-knots, known as the anti-knots, also separated by lambda over 2 meter. Okay, this is also lambda over 2 meter. Okay, similar this one, lambda over 2. Okay, the distance between knots and also the distance between anti-knots is lambda over 2. And this is the animation of standing wave. So you're going to see that assuming that the yellow color is the incident wave. So assuming that the source is over here and the load is over here. Okay, so the yellow wave is moving from left to the right, and this is the incident wave, and the gray color wave is moving from left to the right, from load to the source, okay, which is the reflected wave. And the purple color wave is what we call as the standing wave. Okay, so you see that if we freeze the time, for example now, so you can see that it looks like a standing wave, as if there's a wave stands on a flat surface. Okay, so ideally, we don't want this standing wave, ideally. So if there's no standing wave, it would be better. That means we have a matched transmission line. Our objective is actually we want to have a matched transmission line, which is the best case scenario. However, if there's a unmatched transmission line, of course, there's going to be a reflection, a losses, okay? Some losses. So because of these losses, since we have unmatched transmission line, for unmatched transmission line, ZL not equal to characteristic impedance, so that means there's going to be reflection. So since there's a reflection wave, so there's another parameter, what we call as the reflection coefficient. Reflection coefficient is equal to ER over EI or IR over II. ER is a reflected wave voltage divided with incident wave voltage, or reflected wave current divided with incident wave current. Okay, so this is a unitless parameter. Okay, the reflection coefficient is a unitless parameter. So there's three scenarios. There are three scenarios over here for the matched and unmatched transmission line. So this is scenario number 1, scenario number 2, scenario number 3. Okay, so I want to go through scenario number 3 first. Scenario number 3 is when the load impedance equal to the characteristic impedance. This is what we call as match. Okay, match transmission line, where all the incident wave is absorbed by the load. That means there's no reflection. So if no reflection, that means the reflected parameter is equal to 0. Okay, so and then we go back to the first scenario. Okay, the first scenario, open circuit. That means the circuit is open at the load side. Okay, so this is the source, this is the load. So the load is open. That means the load impedance is infinity. Okay, so in this case, the reflection coefficient is equal to, so you can put inside the values, so you get equal to 1. That means total reflection occurs. That means all of the incident wave will be reflected back to the source. Okay, so that's why the name is it is said as total reflection. Another, if we go to the second extreme cases, short circuit. Okay, short circuit means that it is at the load side, the conductor is shorted like this. Okay, where this is a source, this is the load, and in this case, that means the load is equal to 0. Okay, so this is the short circuit scenario. In this case also, total reflection occurs. That means all of the incident wave will be reflected back to the source. However, the reflection is 180-degree out of phase. And in this scenario, that means the reflected parameter is equal to -1. Okay, for short circuit transmission line. Okay, so there are three extreme cases: the matched transmission line, and also open circuit for unmatched transmission line, and short circuit for unmatched transmission line. So if we go back to the standing wave phenomena, okay, for the standing wave phenomena, where remember that standing wave only happen if load impedance not equal to characteristic impedance. Okay, standing wave only happen if load impedance not equal to the characteristic impedance. Okay, so this is a transmission line for the open circuit. Okay, open line. Open line is for the open circuit. If you see from the previous slide, open circuit, that means the load impedance is infinity. That means we're going to have total reflection. Okay, reflected parameter is equal to 1. Okay, so if you see from here, the source is on the left, the load is on the right. Okay, so in this case, you're going to see there's a two line here. So the blue color line is the voltage line, the voltage of the standing wave. Okay, so remember, the blue color line and also the dotted line is a combination of incident and reflected wave. Remember, incident and reflected wave produce standing wave. And in this case, we want to see the characteristic of the voltage and current of the standing wave. Okay, so if you see from here, the voltage of the standing wave, so this is an open circuit. At the end, it's an open circuit. Okay, open circuit. That means the voltage, if you see the voltage wave is like this, the voltage wave starting from maxima, okay, starting from maximum, and the current is starting from minima over here. Okay, this is the current. So if you see from here, the voltage of the standing wave at the load side is maxima. Okay, the voltage at the load side is maxima. Okay, and as we move towards the source, okay, as we move towards the source, lambda over 4, you're going to see that the voltage is minima at lambda over 4 distance from the load. And as we move again towards the source, lambda over 4 distance, the voltage becomes maxima. Okay, so that is a characteristic of the voltage. And if you see that the voltage stated here is reflected just as if were to continue no phase reversal. So the reflected voltage, the incident voltage, and the reflected voltage has the same phase, no phase reversal. However, for the current of the incident wave and the current of the reflected wave is different in terms of 180 degree. There's a shifted in terms of phase. So the current, if you see from here, the current of the standing wave is minima at the load side, okay? And the current is when we move towards the source, lambda over 4 distance, the current is maxima. And if we move another lambda over 4 distance towards the source, you're going to see that the current is minima. Again, another lambda over 4 distance, the current would be maxima. Okay, so this is the changes of voltage and current of the standing wave as we analyze from the load side towards the source. Okay, so this is for the open line. And for your information, we have asked this question previously in the previous semester about standing wave in the open line or shorted line. Okay, so this is for the shorted open line. And another one is a standing wave of a shorted line. So shorted line means that the line is shorted. Okay, the line is shorted at the load side. Okay, so this is the load on the right, the source on the left. So in this case, of course, Z load is not equal to characteristic impedance. Okay, that means there's going to be total reflection from load to the source. Okay, none of the power is absorbed by the load, so the voltage is reflected 180 degree between incident and reflected wave, while the current has this, the incident current and the reflected current has the same phase. So the sum of the incident and reflected current waveform is maximum at the short. The sum of the incident current is maximum, okay, which is this one. Okay, the sum of the incident and the reflected current is maximum at the load side. As we move towards the source, you're going to see that the current, the sum of the current is minimum. And as we move further away, lambda over 4, you're going to see that the current is maxima. Okay, remember the current is actually the current of the incident plus reflected wave. Okay, which is the current of the standing wave. So, and then the sum of the incident and reflected voltage is minimum at the shorted voltage, shorted load. So that means you see that the voltage is minima at the load side, and as we move towards the source lambda over 4 distance, the voltage is maxima. And as we move again lambda over 4, you're going to see that the voltage is minima, and so on. As we move further away, the voltage is maxima again. Okay, so this is the pattern of the standing wave. Maxima, minima, maxima, minima, depending on the distance from the load towards the source. Okay, so remember the current here, okay, the current and the voltage here is actually the summation of current and also the voltage of the current of the incident and reflected wave, and while the voltage is the summation of voltage for the incident and reflected wave. Okay, remember each line here, the blue color, the voltage line is the summation of voltage, incident and reflected wave, while the dotted line current here is the summation of incident and reflected wave. Okay, because we are talking about standing wave. So remember, standing wave is a combination of incident and reflected wave. You have to combine both, standing incident and reflected wave. It becomes the standing wave. So this is the slow motion of how the incident wave happens from picture A until picture N. Okay, so initially the wave travels from source to the load. Okay, so when the load is unmatched, if the load side is not equal to the characteristic impedance, what happens is that there's going to be reflection. So this is a slow motion movement of the wave. So you see that the reflection happens. So and then you're going to see the reflection. So reflection here is a reflection and the reflection through. So we're going to see that how the reflected wave happens. Okay, so you see that the dotted line here is the reflected wave. And finally, if we freeze the time, we're going to see that the wave is a standing wave like this. The standing wave here is the combination of incident and reflected wave. And then a standing wave ratio. Standing wave ratio SWR is defined as the ratio of maximum voltage to the minimum voltage of the standing wave, okay, on the transmission line. Often called as a voltage standing wave ratio, VSWR is a measure of mismatch between the load impedance and characteristic impedance of the transmission line. So Vmax is equal to EI plus ER. Voltage of the incident wave plus voltage of the reflected wave. Divide with Vmin. Vmin here is voltage of the incident wave minus voltage of the reflected wave. Okay, so we get this is a unitless parameter. And the relationship between SWR and the reflection coefficient, you're going to see that VSWR, we know that this is Vmax over Vmin, which is EI plus ER, divide with EI minus ER. And the reflected parameter is ER over EI. So if we put inside the parameter of reflection coefficient in the VSWR equations, so we're going to get VSWR is equal to 1 plus reflected parameter divide with 1 minus reflected parameter. Okay, so this is unitless parameter. This is a unitless values. Okay, 1 plus reflection coefficient divide with 1 minus reflection coefficient. So you're going to get the VSWR. So rearrange the equations. We can get the reflection coefficient equal to VSWR minus 1 divide with VSWR plus 1. So this is also a unitless parameter. So with the load is purely resistive, VSWR can be expressed by Z0 over ZL or ZL over Z0, whichever give the VSWR more than 1. So this is if the load is purely resistive or the matched transmission line. So you're going to get a VSWR more than 1. So the disadvantages of having unmatched transmission line. So what is the disadvantage? Disadvantage here in terms of when the load impedance not equal to the characteristic impedance. So that means 100% of the source incident power is not absorbed by the load. A reflection and another reflection will cause more power loss. So mismatch also cause noise interference. So ideally, we want to have a match transmission line. Okay, that's the ideal scenario. So let's do the example. Example 5, for a transmission line with the incident voltage EI equal to 5 volt and reflected voltage is equal to 3 volt. So reflection coefficient is equal to EI. If you see from which one? This one? So ER reflection voltage divide with a incident voltage. Okay, so that means this is equal to ER divide with EI. So this is 3 volt divide with 5. So you're going to get 0 0.6. Okay, 0 0.6. Okay. And then VSWR. VSWR is equal to Vmax divide with V min, right? So if you see this one, Vmax over Vmin, that means EI plus ER divided with EI minus ER. Okay, so that means EI plus ER divide with EI minus ER. So this is 5 plus 3 divide with 5 minus 3. So you're going to get 4. Okay, so this is the answer actually. Okay, so example 5 is straightforward. Okay, so until example 5, this is related to the transmission line. Okay, and as we move to the next topic, the antenna. Okay, so this is the next big topic, the antenna. Antenna is a metallic conductor capable of radiating and capturing the the electromagnetic energy. So the function of antenna is to radiate and also to absorb the wave, okay, the electromagnetic wave. So if you see from here, uh, we have a transmitter antenna on the left side over here. So the source here generates the signal. Okay, the transmitter here generates the signal and pass through the antenna over here. The antenna will radiate the signal. So theoretically, the wave will travel in the form of spherical. Okay, theoretically, the wave will be transmitted in the form of spherical, like this. Okay, so it is known as spherical wave. And as the wave travel at long distance, okay, we're going to see that the wave looks like as if it is a straight line like this, and this is what we call as plane wave. Okay, so this is when the wave has traveled at much longer distance. Okay, and the receiver antenna will absorb the wave and do the next process to produce the original signal. So antenna has a few sets of parameter. Okay, it has a few sets of parameter. So antenna efficiency is equal to P radiation power, divide with the input power. Okay, so if you see from the previous picture, for example, in the transmitter side, okay, so P input is the power input to the antenna, P input, while P radiation, okay, while the power that we need to radiate the wave into the medium is what we call as P radiation, sorry, P radiation. So P radiation is the power that we use to radiate the wave into the wireless medium. Okay, of course, you're going to see that the P radiation is less than the P input. If the P radiation is the same as P input, that means we're going to have 100% efficiency. Okay, so if you see from here, some of the wave will be dissipated as heat. Okay, so that's why the P radiation is less than the P input. So the antenna efficiency is equal to P radiation divided with the input power to the antenna multiply with 100%. So you're going to get efficiency in terms of percentage. So if you see from here, the P input is equal to P radiation plus PD here is the dissipated power as heat. Okay, so PD here is a dissipated power in the antenna. Okay, and this is the radiation resistance. So imagine that this is an antenna shape. This is the antenna shape. So where the antenna has uh, R effective RE, and this is the R radiation. Okay, radiation resistance over here, and another radiation resistance over here. So this is the effective resistance in the antenna. So if you want to measure uh, the efficiency, also can be calculated as R radiation divide with R radiation plus R effective. So we can assume this is the second equation to find the uh, antenna efficiency. Of course, you have to multiply with 100% in order to get the value in terms of percentage. Okay, so normally efficiency is written in terms of percentage. And then we can see the isotropic antenna. Okay, so for your information, isotropic antenna is a theoretical antenna. It doesn't exist in the real world. Okay, so isotropic antenna is commonly used as a reference antenna when we design the real antenna. Okay, for example, you want to design a real antenna, so you will make a comparison. Okay, you will refer to the isotropic antenna as the benchmark. Okay, so this is a theoretical concept of antenna, isotropic. Okay, so if you see that isotropic antenna or isotropic radiator is a point source that radiates electromagnetic energy at a constant rate in all direction. Okay, so you see that the isotropic antenna is this one, is a point source over here, where it radiates the wave in all directions. So since it radiates the wave in all directions, we're going to see that the shape of the transmitted wave looks like a spherical wave. Okay, so it looks like a spherical wave of transmission. And another parameter for the isotropic antenna is the gain. So the gain of the isotropic antenna, GP, is equal to 1. So GP is a power gain. D or GD is a directivity gain. Okay, so the gain for the isotropic antenna is equal to 1 for both GP and directivity gain. Remember, for the antenna, it has two types of gain. The first one is power gain. The second one is the directivity gain. Only for isotropic antenna, both GP and directivity gain is equal to 1. Okay, so remember, for isotropic antenna, it radiates the wave in all directions and the gain is equal to 1. Okay, so this is the two main characteristics of the isotropic antenna. And if you see from here, the directivity gain, the antenna, okay, so the antenna gain, we have two kinds of gain. The first one is directivity gain. So if you see from here, directive gain is the ratio of power density radiated in a particular direction to the power density radiated to the same point by a reference antenna, assuming both antenna are radiating at the same amount of power. So what is this actually? So if you have a real antenna, okay, if you have a real antenna, this antenna uh, radiates a wave, okay, towards this distance, okay. So the power density at this point is P. This is P. Okay, this is PD, the power density by the real antenna. And you compare this with a isotropic antenna. Okay, this isotropic antenna also use the same radiation power, P radiation. Okay, this is a P radiation. So the wave also sends until this distance. Okay, so you're gonna get P reference over here, the power density at this point. When you compare how much is the power density between the real antenna and the power density produced by the reference antenna, which is the isotropic antenna, so you're gonna get the directivity gain. Okay, so directivity gain is the ratio of power density produced by real antenna divided with the power density produced by the isotropic antenna. Okay, so power density is watt per meter square. Okay, so watt per meter square divided with watt per meter square. So you're gonna get D is a unitless parameter. Okay, so in some other literature books, they use the symbol of GD parameter. Okay, GD parameter in some other literature books. Okay, another type of gain. So we know the first one is directivity gain. The second one is the power gain. So what's the relationship between power gain and directivity gain? So power gain is equal to directivity gain multiplied with the efficiency. Okay. For example, if the efficiency is 90%, efficiency of antenna is 90%, that means your GP is equal to 0.9 of directivity gain. Okay, so in most of the cases, you're going to see that power gain is slightly less than the directivity gain, depending on the antenna efficiency. Okay, so it's already 2 o'clock, so we can take the attendance now. So you can open your QR code and you can scan the attendance. Okay. So you can scan your attendance and you can go to another class. So see you again next week. Okay, next week will be physical class. Okay, and don't forget to do your project activities. Okay.
Thank you, Doctor.
Okay, welcome.
Okay, thank you, Doctor.
Thank you,
Okay,
Doctor.
welcome. Welcome.
Bye-bye, Doctor.
Thank you, Doctor.
Thank you,
Okay,
Doctor.
Merry
welcome. Okay,
Christmas.
welcome. Bye bye.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Assalamualaikum, Doctor.
Waalaikumsalam. Yeah.
I could not took my attendance.
Can you take it manually?
What's your name?
Mujahid Abdullah.
Mujahid. Mujahid.
Yes. Yeah.
Mujahid. Okay. Okay, done.
Okay. Thank you, doctor.
Okay,
Me
welcome.
also Dr. Usman Mirgan.
What's your name?
Usman Mirgan.
I cannot see your name. What's the name?
Usman Mirgan.
Osman. Okay. Okay, done.
Thank you, Doctor.
Okay, welcome. Okay, dah scan semua? Sekejap eh. Okay, scan your attendance. Everyone.
Okey, dah doktor. Terima kasih. Maaf.
Okay, sama.